Right. So last two sessions we had actually were recording sessions, right? So in Thursday's session, I had shared a small video on noise equivalent bandwidth, and I had assigned it in Canvas through Edpuzzle, and I could see most of you have not even watched it, right? I appreciate some of you have like turned in the open-ended, answered the open-ended question, right? And others, I could see most of you have not watched, right? So, right, I request all of you to watch the videos assigned in during offline sessions regularly. Otherwise, you won't get the continuity, right? So today, what I'm going to discuss, it's a continuation of that. Some of the aspects which we have discussed there will be used here. So those who have not watched, right, they'll definitely get disconnected. So, right, so I'll excuse for this time. Right. So maybe from next time, I request all of you to watch. You had 2 days of time, right? Even yesterday, right, I had asked you to watch some more video along with that on PLL, right? So that PLL, right, I'll take it as a self-learning topic, right? So you can, I've made the video available. You can go through that video, and the textbook material also I'll make available, right? So what we'll do is we'll have a maybe somewhere in the next week, right? We'll have a quiz. Along with the quiz, I'll discuss the important aspects of that. Right. So after while discussing the answer key to that quiz, we'll discuss the important aspects. So that quiz will be a graded quiz for you people. So right, please try finish watching that videos as well. So, and one more thing which I want to tell is as and when you watch this, try to take down some lecture notes, which will definitely help you out. Right. So yeah, so that's it. With that note, we'll start today's session. So we were discussing, like we were in module 3, we were discussing about actually what noise, right? So in this module, we have to study the noise performance or a sort of comparison of different AM and FM schemes. This is what we have to, right, whether my screen is visible, what I'm writing, all of you are able to see. Can anyone give me a quick feedback?
Yes, sir.
Yeah, okay, okay, fine. So it gives some, I am experiencing some sort of delay here. That's why I asked. Right. Yeah, okay. So AM and FM. So this noise performance of AM and FM. So for that, some of the basics, right, what we have discussed so far, right, um, how to model different noise processes. We have seen how to model thermal noise, short noise, and in general, right, an idealized white noise, right. So in further discussions, right, we'll be modeling the noise process and additive white Gaussian noise process. So right, for that, right, you should be familiar with the aspects such as power spectral density, right? What if you give certain power at the input of an LTI system, what will be the output power, right? And yeah, so autocorrelation function, all those aspects which we have discussed, that those are the prerequisites for you to appreciate these forthcoming topics, right? So topic would be noise in AM and FM. So in last class, what we have seen is noise equivalent bandwidth. So in some textbook, they are referring it to as NEBW, right? So this noise equivalent bandwidth is the bandwidth. How it was defined as it will be the bandwidth of an ideal filter, right? An ideal filter with a rectangular frequency response, be it a low pass filter or a band pass filter or whatever it is, right? So response of an ideal filter, which will give bandwidth of an ideal filter, which will give same power output, noise power output as that of any arbitrary filter. So we have considered the example of an first order RC filter, RC low pass filter, and that of an ideal low pass filter. So that was an open-ended question. As most of you have not give an answer for that, I'm not going to discuss that. But some of the aspects which you should know for this discussion, like for this particular topic, I'll be discussing. For that, right? So I'll we'll take it up as a Q&A session, right? I'll ask some questions, you have to give me some inputs. So what do you mean by white noise, right? What do you mean by white noise? So can anyone, can you please type it in? So why? Because in further sessions we'll be modeling the noise as white noise process, additive white Gaussian noise process. So when I say white noise, right, what are the points which come to your mind? So Sherwin has typed all frequencies. Then other points, if I may ask, the power spectral density of white noise, double-sided power spectral density of white noise, what would be the answer? Yeah, please do type in. Right. Sherwin has typed all frequency. Then other things. Uh, White noise is a noise whose power spectral density is uniform over the entire frequency. Excellent. Yeah, it's uniform over the entire frequency, which means it has all frequency. Noise produced by signal containing all audible frequencies of vibration. It's not only audible frequencies, right? So whichever be the system we are considering, even if it is we are discussing audio frequency range or radio frequency range or even microwave range. I'm telling to Swaroop. Swaroop has typed all audible frequencies of vibration. It's not only audible, right? It need not be audible frequencies. It's all frequencies, right? Okay, fine. So the Poisson density, it is equal to n naught by 2. So I was about to actually draw that Poisson density, right? We represented it as SW of F, and as Shreyas told, it's uniform over all frequencies. It is equal to n naught by 2, right? Then if we pass this white noise through an ideal low pass filter, right? Ideal low pass filter of bandwidth B. So when right? So this is an actually what transfer function of an ideal low pass filter, right? If you pass this a white noise through an ideal low pass filter, what is the output? How to find the output, right? The output will be, right, or Sn of F, output noise power spectral density will be SW of F into mod of HLP of F square. This is what we have learned, right? So this is a very important result, and we have seen if this is equal to, if the passband gain of this low pass filter is equal to 1, right? If this gain is equal to 1, right, then this will be SW of F, and the problem is actually what, it will be defined only from minus B to B, right? So this can be modeled as this, right? 0, B, and this will be n naught by 2, right? This Sn of F will be output noise power spectral density will be n naught by 2. Now my question is, right, what will be the total power output? Pn we have seen it will be integral from minus infinity to infinity. Please note down all these points. These points are very important, and if you can appreciate these things, then the forthcoming discussion will be very easy for you. Otherwise, it's going to be Greek and Latin, right? It's a very simple concepts. I'm repeating it many times. Why? Because it's important, right? So total noise power will be equal to, if you integrate power spectral density from minus infinity to infinity. So this is a very important result. Power total or average power can be obtained by integrating power spectral density from minus infinity to infinity, or we have also seen it is equal to what, it will be equal to what, control Z, Rn of 0, right? Autocorrelation function at tau equal to 0. This is also true, right? So I'm not, right, I'm not discussing about autocorrelation function now, right? So we'll concentrate on this power spectral density. Why? Because we are given with noise power spectral density, right? So from that we can find out Pn like this. So this will be equal to, right, if you integrate it, right, if you integrate n naught by 2 from minus B to B, right? So this is equal to anyhow minus infinity to minus B and plus B to plus infinity. At these points, for these values, it's equal to 0, right? So we can rewrite this integral from minus B to plus B n naught by 2 df, right? And this will be equal to n naught by 2 times, right? Integral df is f, if you apply limit plus b and minus b, it will become 2b. So this is equal to n naught b. So this is again important. This will be directly using n naught b or n naught bt. So if you write the transmission bandwidth as bt, right, plus bt and minus bt. So in further discussions, I'll straight away tell the noise power output at an ideal band pass filter or ideal low pass filter is actually what, n naught times Vt, where N naught is actually what, power per unit bandwidth. The N naught will be power per unit bandwidth. So even though, right, the power within positive frequency is N naught by 2 times B, right, but we are assuming, right, its power is equally divided among positive and negative frequency. And the significance about positive and negative frequencies, if you remember, we had a very detailed discussion. Some of you have come up with very wonderful actually what insights, right? So here again, right, so we'll be considering double-sided PSD, power spectral density. We will have positive and negative frequencies, but when it comes to total power output, you can see it considers actually with the negative frequency also, and it is n naught bt, right? So this is again very important result, right? So instead of this, if you pass this ideal white noise, right, SWFF0 through a ideal band pass filter, right, through an ideal band pass filter, right, which I'll just draw it like this, an ideal band pass filter. So again, I have to draw actually what, double-sided frequency. So this is right. Say it this response is centered at say FC, right? It's spanning from FC plus BT. Sorry, FC plus BT by 2 to FC minus BT by 2, right? On both sides. Negative frequencies I am not showing. This is actually what, a frequency response of an ideal band pass filter. So if you pass, right, so this again, this is also B, this much is also B, and this much is also B, right? And the magnitude, passband magnitude will be equal to 1. So in this case, can anyone tell me what will be the output, power output? Or you should tell me what will be output noise power spectral density Sn of f, and what will be Pn, right? I want you to tell me how to find that. You can just type it in how, right? If you understood this, if you can give answer to this, then remaining portion simply you can only just read through. If I give you notes, you can simply read through the remaining topics, right? So this is the critical aspect which you should appreciate. It's not critical. Only problem is, right, when I say average power spectral density, there is a problem in visualizing it, right? That, right. So the only issue is this concept as such is abstract. Otherwise, right, these are okay. So now my question is, the if you pass a white noise through a band pass filter, why? Because in next, when I'm discussing receiver modeling, right, so there will be a band pass filter before the demodulator, right? So when I say this additive white Gaussian noise contaminated signal is passed through a band pass filter, the output, I'll say it is the noise power is this much, right, and signal power is this much. When I say that, right, you should be able to appreciate. That's why I'm asking, if you pass this white noise through a band pass filter, right, if you pass this white noise through a band pass filter, what will be the total power output? Band pass filter exactly as shown here. I've drawn the response of band pass filter. So this is actually what frequency response of a band transfer function of a band pass filter. This is PSD of white noise. What will be Sn of f, and what will be Pn? Yeah, I'll give you a 1 minute time. You can just try it out and give me answer. All of you have to try. Yeah, please, last. Okay, I'll give 1 more minute. Why? Because you will have to perform some integration. Right, it takes some time, of course. Right, and So here, just listen here, while evaluating from minus b to b, what you can do is, as it is an even function of frequency, instead of integrating from minus b to b, you can integrate it from 0 to b, and twice of that integral, n naught by 2 times df. Right, this will also give same result. So similarly, here in the case of band pass filter, when you are integrating from minus infinity to infinity, from minus bt fc minus fc minus bt by 2 to fc minus bt minus fc plus bt by 2, it is non-zero, and in this interval it is 0, right? Instead of that, you can integrate it from 0 to infinity and take twice the result what we are getting. It will give you same thing. So what does that? We are not getting any answer yet, right? Are you all trying, or should I only discuss that? Right. It should not be a waste of time, right? So some people may be trying out, some people may be what? Simply sitting, right? They may not even know what is happening here. Are you all trying, or shall I proceed with the discussion? Right. I don't want to. Yeah, why? At least do let me know if you all are trying. Right. So meanwhile, I'll just take attendance. Right. Today I'll just call out the attendance. Abhilash, please say yes if you're present. Abhilash? Absent. Abhirama? Aishwarya? Ansar?
Present, sir.
Abhilash, yeah, your turn is done, Abhilash. Right.
Hello, sir. I'm Abhilash.
Anup?
Yes, sir. Present, sir.
Hima?
Present, sir.
Kiran?
Present, sir.
Manoj?
Present, sir.
Pratibha?
Present, sir.
Rayan?
Present, sir.
Sanjay?
Present, sir.
Sherwin? Sherwin Ravi and Sherwin Brian, both.
Present, sir.
Okay.
Present, sir. Present, sir.
Okay, you people are there, right? I just wanted to know, right? That's why. So now some messages started coming, right? It's present, sir, right? Yeah. So, okay, let me ask a question frankly. Are you able to understand what actually is being discussed? When I say noise, it's power spectral density. Be frank, right? Be frank, right? When I say noise, it's power spectral density, right? So some of you may be thinking, yesterday I posted a video and those who have not seen won't be able to understand. It's not that, right? That's why some of the important aspects I'm discussing again, right? We have time, right? So we'll, right, discuss the aspects and move forward slowly. Please don't think if those who have missed the previous video won't be able to understand. It's all about your mindset, and right. So please do pay attention here, right? So this power spectral density, it is nothing but what, right? On x-axis it is the frequency, and y-axis for each frequency component, what is the power level, right? When you take Fourier transform, right, it will give you what is the magnitude of each frequency component. If it is direct Fourier transform, when you are converting a signal or a transfer function into its frequency, or impulse response into a frequency domain, it will give you, it will speak about magnitude. So here we are interested in power, output power, noise output power, all those aspects. So that's why we are dealing in terms of power spectral density. Power spectral density simply is actually what? For each frequency content, what is the power level, right? it gives that for each frequency content what is the power level, right? So it's just like maybe I can give an analogy for you people, right? I'll plot a graph like this, right? So this is time, right? And on x-axis it is the uh, temperature, right? Not temperature or traffic density or whatever, right? Uh, so if the graph is like this, right? Suppose the graph is like this, right? From this graph, what can intuit, right? This is traffic density. It's actually what number of vehicles, right? Number of vehicles present, number of vehicles per second, right? So there is a very busy road, right? There is a very busy road through which vehicles are passing, right? So this traffic density is number of vehicles per second. Number of vehicles per second is given on y-axis, and time is given on x-axis, right? So suppose you want to find what is the number of vehicles passed between 10 a.m. and 12 p.m. or 12 noon, right? Or 12 p.m. or whatever, right? How you will find that from this graph? I told this is traffic density, which is number of vehicles passing per second, right? Number of vehicles passing per second. So at 10 a.m., say the number of vehicles passing per second is say 20, right? And at 12 p.m., the number of vehicles passing per second, it is reduced to actually what? 17, right? So at each instance, right, there is some, I've shown it as a continuous value. It need not be continuous. It can be discrete also, right? If it is discrete, you will have to what? Literally sum up. If it is continuous, you will have to integrate. So how you will find out the total number of vehicles passed through this road between 10 a.m. and 12 p.m.? You have to simply find area under this graph, right? With this area of the shaded region. How you will find that area? How you will find area of that shaded region? So I'll write it as actually what? Time density as a function of time, TD of t, right? TD of t means time density. It's a function of time. It's not a constant. It's a function of time, right? So total vehicles, how you will find total vehicles passed? How you will find total vehicles passed? This will be equal to, right? So integral from 10 a.m. to 12 p.m. right? Then this TD of t dt, it will give you total vehicles passed. It's actually what? The area under the shaded region. So similarly, right, when you are passing the noise having power spectral density like this, right, the power falling within, like the power falling within a bandwidth of this much, right? Within a bandwidth of this much will be equal to what? Area under this power spectral density curve, right? So it is actually power spectral density is power per unit bandwidth. So it's a, when it's a double-sided power spectral density, you have to consider actually what? Both positive and negative frequency. Only that is power spectral density, right? So why we are talking about power spectral density is actually what? It's right, noise variance, right? So maybe in higher semesters you will study, when you study about actually what AWGN model of a channel, that itself is a module for you, right? There you learn how to find these power spectral density of noise, all those aspects. So here, right, those derivations are beyond the scope of us discussion. So that's why, right, I'm just giving you the general explanation, right? So I hope that is clear now what is power spectral density. So the power distribution, right, over frequency of this particular noise is like this, right? It's constant power for all, right? It's a uniform distribution, as Shreyas told, right? Uniform distribution, right? So now, if this is the case, what will be the power output if it is passed through a system having this much bandwidth? So that will be area under that. So area, how if it is a continuous graph, how you will find out area? You have to integrate. If it was discrete function, you could have taken actually what? Summation. And if it is continuous, it is integration. Right, that's what we have done so far. So in this case also, right, if you integrate it, right, it will be from actually what, fc minus bt by 2 to fc plus bt by 2 n naught by 2. So this again will be equal to what, n naught bt, right? The answer to this again will be equal to n naught bt, right? It depends upon the say bandwidth of the system through which it is getting passed. So in further sessions, our aim is to what, compare the noise performances of DSBAC and SSB, VSB, and FM receivers. Right. That is what we are trying to do. So whichever, as we initially when we discussed, we told FM has better noise performance. Right. So you all actually what, even in exams you have written FM has better noise performance. So how to quantify that, right? How to do a quantitative comparison, that is what we are trying to do here, right? So before we do that, we need actually what, whenever before like mathematics, this is like this part again is mathematical modeling, right? Before we start with this discussion, we need a receiver model, right? So for that, we'll be assuming S of t is our modulated signal, right? S of t is our modulated signal, and W of t, right? W of t is an additive white Gaussian noise, right? So when I say additive, what happens is this noise will get added to our S of t. It's not like what, getting multiplied, or it's not right, right, being taking actually coming as exponent of the S of t. It's actually what, getting added. That's why it's additive. When I say white, it implies actually what, all frequency is there. When I say Gaussian, right? So this probability density function, we won't be using probability density function as such. So if it is Gaussian, right? If a Gaussian random variable you might have studied, if the mean is mu and variance is sigma square, right? Say p x of x, the probability, right, the probability that the Gaussian random variable x to take a value small x is given by 1 by sigma root 2 pi, right, e power minus x minus mu the whole square divided by 2 sigma square. So this is right. So the probability density function, it will be a Gaussian bell, right? So if mu is equal to 0 and sigma square equal to 1, then that becomes actually what, normal distribution table. In mathematics you might have used it, right? Normal distribution table, right? You can find the probability between z equal to this and z equal to that. So from that table, so that, right. So that's, so we can model the noise process or the random signal as a Gaussian process, right? So this noise is a Gaussian process. We'll assume this S of t, it is actually what, a sort of deterministic, right? S of t, or deterministic, or it's a stationary process. W of t is completely random, right? So when a random process is getting what, associated with a deterministic process, the resultant process will become random. So you don't have to bother about this. I just told you, right? So why it is Gaussian, right? So that is additive white Gaussian noise process, right? So now at the receiver, so we are transmitting S of t. So in previous modules, we have studied about AM receivers, FM receivers, and all those things. At that time, did we discuss about noise? No, we didn't discuss about noise. We were assuming it was a noise-free channel, an ideal channel, right? But in this module, what we'll do is we'll assume the noise to be an additive white Gaussian noise, right, process. So our receiver model. So we'll initially start by discussing about receiver model, right? Then we'll discuss what, we'll define some of the terms. Input SNR, right? Then output SNR, right? And channel SNR. SNR, these terms we'll define today, right? Channel SNR, then figure of merit, right? These terms are what we are going to discuss today, right? Along with that, some of the aspects of how a system will behave, right? So this receiver model, right? You can see we have S of t. S of t is our modulated signal, right? This is being transmitted, and at the front end receiver part, you can write it as a plus or you can write it as a sigma. Maybe I'll write it as sigma, right? Sigma. It gets added up with actually what, a wide Gaussian noise process. I'll represent it as W of t, right? It's getting added up with a wide Gaussian noise process, right? So this is plus and this is plus. So this, if you ask me from where this noise came, so this noise can be actually what, uh, the thermal noise or short noise produced in the front end receiver, right? It can be what, the man-made noise which falls within the bandwidth of S of t. It can be galactic noise. It can be anything, right? So the consolidated actually sum of all those things, right? We can model it as actually an additive wide Gaussian noise process. This is actually for our convenience, to mathematically model and find out the limitations, right, and how it will perform, right? So in practice, if you ask me, is it actually whether the noise will be exactly Gaussian and not, right? So it's right, but it's probabilistic, and as it is probabilistic, we can model it like this, right? That's what I mean to say, right? So that is noise. Noise is actually what, W of t, and this noise is additive wide Gaussian noise process, right? And this will be actually what pass through a band pass filter. Right. So I'll discuss about this band pass filter, right? So this band pass filter, right, you can say, um, it actually what represents the combined filtering action. So there will be some tuned amplifiers at the receiving end. So for instance, if you consider FM radio transmission, right? So you right, if suppose if you were using a normal FM radio, you can tune in, right? You can tune in. There will be an indication of different bands. You can tune in, right? So what do you mean by tuning? We have seen different radio stations are using different frequencies, right? So 93.5, 103.2, right? We have discussed all those, right? So if you want to receive a particular radio station, you should tune into that particular frequency. So it's actually what a bandpass filtering, right? It will allow a range of frequencies, right? So that range of so maybe we can model this bandpass filter like this. We can model it as an ideal bandpass filter, whose sender frequency will be actually what, our carrier frequency, whose sender frequency will be our carrier frequency, and it will allow, it will have a bandwidth of actually what, bt. So this will be fc plus bt by 2 to fc minus bt by 2 here, right? I'll write here fc plus bt by 2 to fc minus bt by 2, and on negative frequency side also. So we can model this bandpass filter. We can model, right? So it's actually what, combined effect of the tuning amplifier, or if any other actually what modules if you are using at the receiver end, right? So this bandpass filter is actually what is more, it's a combined effect of all those things, right? So this is so there will be a bandpass filter, right? So after bandpass, so here S of t plus W of t is what we are getting here, right? So input to this is actually what, input to this is S of t plus W of t. So this S of t plus W of t, if it is passed through this bandpass filter, right, we'll get something. So that output we'll represent as X of t, right? And this X of t is what is given to a demodulator, right? X of t is what is given to a demodulator, right? So this demodulator, it can be a coherent detector, right? It can be an envelope detector, right? It can be a phase discriminator if it is actually what, a FM transmitted signal. This demodulator can be a phase discriminator, right? Whatever. So these are right. So this is given to a demodulator, and we are getting output signal. Right? So, but just imagine if this W of t in last cases, right, in last two modules, when we studied about AM and FM transmitter and receivers, we didn't bother about the noise. We were assuming this term was equal to 0. But now, right, for us to what, study the performance of that, we are considering a white noise present. So this white noise itself is actually what, completely random. So that randomness, it will be actually what present in the decision also, that it will affect the output also. The decision also will be affected by this presence of noise. So this is the system model which we are considering. So this demodulator can be, in the case of a DSBAC, it will be a coherent detector, right? And if it is right, and similarly, if it is a VSB or SSB, right, it will be um, right. So it's the corresponding detector. If it is FM, it will be the corresponding detector, a phase discriminator or a PLL or whatever, right? So this bandpass filter model for AM or FM, so we'll be assuming this bandpass filter transfer function, it is centered at FC and it allows a bandwidth which allows actually what the band entire range of frequencies present in S of t, right? So this band pass filter will allow the entire range of frequencies of S of t, and whichever be this frequency range the band pass filter allowing, our white Gaussian noise process will affect. Why? Because white Gaussian noise is present for all, is applicable for all frequencies, or its power spectrum is uniform function, right, over minus infinity to plus infinity, right? So it will be variable. So this is the um, receiver model. So and this x of t, we can write this x of t as S of t, right? So we are assuming if S of t is passed through this band pass filter, S of t won't be affected. Why? Because if S of t, this band pass filter will allow the entire S of t as such, right? So S of t will be S of t as such, but this W of t when passed through this band pass filter, we'll represent it as N of t. Why? Because W of t, right, it was like this, but after we pass it through a band pass filter, right, it will be the N of t will be right like this. N of t will be like this. It will pass only frequencies from say fc minus bt by 2 to fc plus bt by 2 on both positive and negative sides, right? So this is how we can model x of t. So you can see here we have message modulated signal and the noise, right? Filtered noise. So this N of t is nothing but what? Filtered noise. This N of t is nothing but filtered noise. S of t is again modulated signal. So this filtered noise, right, we can represent it using its canonical form, right? This N of t. I am not discussing what is sorry canonical form, but it's like you can represent it as in phase and quadrature phase component, right? So Ni of t cos 2 pi fct minus Nq of t sine 2 pi fct. So this is actually what canonical form of this bandpass filtered noise. So this Ni of t is called actually what? In phase component, and Nq of t is called actually what? Quadrature phase component. So maybe you can draw some analogy to what? Quadrature carrier multiplexing. So right, but in this in detail you'll study in actually what? 6M, right? So we don't have to discuss this in detail. So it is a continuation of whatever that Hilbert transform and complex envelope, all those aspects which we have discussed, right? So, but I don't think we have to go that much into that depth, right? So just you can keep this in mind. So it can be represented in canonical form. I'll write it here. It is actually what? Canonical form, like this. It can be represented in canonical form like this. So please, right, along with me only, please note down these points, right? So that, right, as I'm taking time and writing on this whiteboard, I believe you'll also get time to what? Note down these points. If you have not taken it down, right, then it's not fair. Now, so this is the receive model, and this x of t is what is transmitted through is passed through this demodulator, right? So this x of t has a signal part and a noise part, right? So the total power within x of t, right? The total power within x of t is that of signal plus that of noise, right? So if noise power is more, what happens is we won't be able to reliably demodulate it. Even if we demodulate, we'll get something else, right? So you might have right heard of actually what mobile phone jammer and all, right? Mobile phone jammers and all. What it does is actually what it right transmit very high frequency noise, right, in the intended range of the range of frequencies which is used for that particular uh, communication system, right? So that it can actually what uh, tamper with the signal and it will affect the reliable like detection. So any system, right, it will perform right reasonably if the ratio of signal power to noise power is above a certain threshold, right? If signal to noise ratio, right, that's if it's below a certain level, then that system can't work perform reliably, right? So that's so now I'll introduce you to some terms, that is SNR, right? This SNR is nothing but what signal to noise ratio, right? So signal to noise ratio at the input, right? Signal to noise ratio at the input is actually what the ratio of average power of the modulated signal to average power of the filtered noise n of t, right? So SNR input, so we can write it as SNR of I, right? SNR I, this is the ratio of average power of modulated signal, that is average power of S of t to average power of filtered noise, right? That is n of t. So SNR input SNR, right? Input SNR is actually what SNR at the input of demodulator, right? Input SNR is an SNR at the input of demodulator. That is actually what after the bandpass filter, right? What here we'll be measuring input SNR, right? Input SNR is SNR at the input of demodulator. That is actually what average power of S of t by average power of n of t, right? So we know how to find average power, right? So that's what we have been discussing so far, finding average power from power spectral density, right? We know how to find average power. So this is one aspect, and a more useful measure is actually what SNR at output. A more useful measure will be SNR at output, right? So SNR at output, it is defined as actually what as a ratio of average power of the demodulated message signal to average power of the noise, both measured at actually what the receiver output. So SNR output is average power of demodulated message, demodulated say message signal, right? Demodulated message signal to average power of, so average power of noise, right? We should measure it output of receiver, right? This measurement we have done actually what input of modulator, right? SNR input we measured at actually what input of modulator, and SNR output we are measuring at the output of modulator, right? SNR input is measured at input of modulator, SNR output at output of modulator, right? So then uh, we will discuss some of the aspects of this additive wide Gaussian noise again, right? This additive wide Gaussian noise, right? This W of t, as we know, right? As we know, it has its possible density is n naught by 2, right? Possible density is n naught by 2, defined for both positive and negative frequencies, right? Then this N naught is actually what? Average power per unit bandwidth. The N naught is actually what? Average power per unit bandwidth, right? N naught is average power per unit bandwidth, and we can also assume this mean is equal to what? Mean of this is equal to 0. So now our aim is, we have a, so right, I'll just redraw the receiver model again. This is S of t and this is W of t, right? So this is given to a band pass filter, right? This band pass filter, I told, right? It's actually what it models the cumulative effect of the tuning amplifier or any other amplifier uh, which is placed at the front end of the receiver, right? So it gives x of t, and this x of t is given to a demodulator, right? Demodulator, and we are getting demodulated output, right? So here we are measuring, if we measure the signal power to average signal power to noise power, that is called actually what? SNR input. And here if we measure signal power to noise power, right, that will be SNR output. So next aspect is actually what? Form factor, right? So form factor will be using these parameters to what? Compare different modulation schemes, right? So form factor, it is a ratio of, okay, not, sorry, not form factor, it's actually what? Figure of merit, right? Figure of merit, normally we'll call it a FOM, right? It is defined as actually what? SNR at output to SNR at input. So it's a ratio, or you can say output SNR normalized with input SNR, right? Output SNR by input SNR. This is actually what? Figure of sorry, figure of merit, right? So this is what we'll be using, what, to compare the performance of different modulation schemes. What information it gives, right? So at the input, it had some SNR level, and at the output, the SNR level is this much. So the signal to noise ratio at the output is same as that of signal to noise ratio at the input, right? Then this particular quantity will be equal to 1. Right. On the other hand, after getting demodulated, the signal to noise ratio, if it is less compared to what? Signal to noise ratio at the input, then it will be less than 1. That is not actually what? Desirable, right? And if signal to noise ratio is better compared to input, then that will be greater than 1. So this is desirable, right? We should get actually what? Better. So figure of merit should be, right, if figure of merit is very good, very high, it means a system is actually what? A very reliable system, right? So figure of merit, if you are asked to define figure of merit, it's actually what? Output SNR normalized by input SNR. That is actually what? Figure of merit, right? So now, in next class we'll start discussing about actually what a noise in DSBSC receiver, right? For that, the system model will be like this. So we have S of t, right? S of t will be what? C of t into M of t, right? C of t into S of t will be C of t into M of t. This will be contaminated with additive wide Gaussian noise, W of t, right? So it will be passed through a band pass filter, right? Depending upon the modulation scheme which we are considering, the band pass filter will change. But our DSBSC, if you remember, the spectrum was like this, right? That is centered at FC, and FC plus FM or FC, right? FC plus FM and FC minus FM, right? FC plus, say, total bandwidth by 2, or FC minus total bandwidth by 2. So we can have a band pass filter as discussed, right, previously. It will be centered at FC, right, and it will allow the entire frequency. So there is a band pass filter, and the demodulator will be actually what, a coherent detector. So here we'll have a local oscillator producing a carrier cos 2 pi fct, right? So for convenience, we'll be assuming this band pass filter is an ideal one, right? And the phase of the local oscillator, right, phase error we are not considering, and amplitude of this local oscillator output we are assuming to be equal to 1, right? So initially we'll pass it through a sorry, product modulator, right? A product modulator. So we can write it as actually what, a product modulator, right? Then we'll pass it through a low pass filter, right? Then we'll pass it through a low pass filter, right? So then we'll get output. So in this case, right? So here it is actually what, x of t, right? So that is s of t plus n of t. So we'll analyze. This is what we are going to analyze in next class, right? So what will happen to a DS, right? So what is the noise performance of a DSB-SC system in presence of additive wide Gaussian noise process, right? So that the basic thing, if this much is a noise at the input, right, what will be the noise at the output? The aspects such as power spectral density, all those things, if you know, right, then maybe within two sessions we can finish the remaining entire topics, right? So that's all about actually what the receiver model, right? And input SNR. So SNR is signal to noise ratio, so signal power by noise power. So if so, a good system, right? A good system should have, right? What should be the SNR? It should be, signal to noise ratio should be high, or signal to noise ratio should be very low for a reliable system. It is signal power by noise power, which should be right. So in numerator we have signal power, in denominator we have noise power, right? So if a system is said to be reliable, or if a system is, right, good, right, what should be the SNR at the output? It should be high, it should be low, or it should be equal to 1. Yeah, you can type it in, right? All of you please type it in. It should be greater than or equal to 1. So it should be high actually, right? It should be high. Maybe right, while discussing, maybe we'll do some simulation. At that time we'll consider some of the actually what practical SNR values, practical BER values, and all we'll consider at that time, right? So it should be very high, right? Be high. If SNR is low, means noise power is more, so then reliable reproduction of the message signal may not be possible, right? So in today's session we have studied about actually the receiver model, a signal to noise ratio at the input, signal to noise ratio at the output, figure of merit. And now I believe you're comfortable with the aspects such as power spectral density. If power spectral density at input to any LTI system with a given transfer function h of f is given, you will be able to find out the output power spectral density. You should be able to find out the autocorrelation function. You should be able to find out the output noise power, all those aspects, right? So I think with that we'll end today's session. So what we'll do is we'll next session we'll start with the noise in DSB-SC system, right? So it's, those are derivations. So what I request is, I request you to what take it down along with me and learn at that time itself, right? So, and please do respond, right? And yeah, your answer sheets I'm yet to share. So today, now, after, right now, maybe within half an hour, I'll share that. Right. If you can just go through, I've corrected it with actually what my pen tablet, so you can, if any right discrepancy is there, if you think there should be some change, you can actually what contact me. I won't share it with everyone. Individual sheet will be shared with individuals. I'm trying to figure out some right means for that. Right. Okay. So that's it for today's session. Thank you so much for joining. If you have any doubt, please feel free to ask. And please do watch the video on noise equivalent bandwidth and videos of PLL. Right. So along with the quiz, we will discuss those aspects. Right. So that's it for today's session. Right. Thank you so much for joining.